Whoa, guys, that sounds great.
Thanks, Selena. Iguki and I are practicing for the annual music festival.
No way, what piece is that?
It's La Campanella by Paganini.
Cool, I've always wondered, why do some notes blend together so well?
Well, a lot of music and harmony can be explained with math.
Tell me more.
Let's start with the basics. What is sound? Sound is vibrations that travel through air. These vibrations cause the air molecules to push against each other, creating areas of high and low pressure. Your ears detect these changes and you hear it.
If we graph this as air pressure over time, we get a sound wave. The frequency of a sound wave is the number of cycles per second, or hertz. The simplest sound wave is a sine wave.
So if the frequency was 5 hertz, that means that the wave went through 5 cycles in a second?
Spot on!
What does this have to do with music?
Well, the musical pitch of a note relates to its frequency, exponentially. The same perceived difference in pitch comes from maintaining the same ratio between two notes.
So 100 to 200 hertz is the same jump in pitch as going from 200 to 400 hertz?
Yep, see the 1 to 2 ratio?
Okay, going back to before, what makes two notes sound good together?
My great piano skills, duh! Kidding.
When two notes are played together, the distance between them is called a musical interval. Some intervals are consonant, sounding nice. Others are dissonant, sounding harsh.
Yikes.
I know, right? For an interval to be consonant, the ratio between the frequency of two notes must be a simple rational ratio.
But why?
It has to do with the period of the resulting wave when two sound waves are combined. With a simpler ratio, the period of the resulting wave is shorter. The shorter periods make it easier for our brains to recognize the pattern compared to a more complex ratio.
1 to 2 is the simplest ratio, and this interval sounds so harmonious that we perceive it to be the same note.
So if I take 440 and double it to 880 hertz, they're the same notes?
Exactly. We call this interval an octave. They're both A, but in different registers.
Fascinating, but how do we decide which notes go on a piano?
On a piano, we want the intervals to be harmonious and be evenly spaced. This way, we can play the same melody anywhere.
This tuning system is called equal temperament. The octave is divided into 12 evenly spaced, distinct pitches called semitones. Each semitone has a ratio of 1 to 2 to the power of 1/12 between each other, which is about 1.05946.
If we go up 12 semitones, by multiplying the frequency by 2 to the 1/12 12 times, we end up with 2, which is just our octave. Doing this with 7 semitones, known as a perfect fifth, we get 1.4983. This isn't exactly a 3 to 2 ratio, or 1.5, but the difference is so small it sounds pleasant.
In fact, if we calculate all the intervals, you'll see they're all slightly off from exact ratios, but really close, all with a percent error of under 1. 12 is a special number as splitting the octave into 12 makes each interval so close to harmonious or simple ratios.
What about this note?
Yup, that one's kind of an exception. The ratio is 1 to root 2, which isn't close to a simple rational ratio, which is why it's the most dissonant interval on the piano.
So while equal temperament tuning isn't perfectly in tune with traditional ratios, these tiny differences are so small that we don't notice them.
Wait, why are there only 12 notes? There are so many more on the piano.
That's right, there's 88, but they're just the same 12 notes repeated by doubling, halving, or quadrupling the frequencies of our octave.
So do all music systems use this 12-note structure?
Nope, in fact, the 12-tone equal temperament system is for Western music. Other cultures developed different tuning systems.
For example, traditional Indian music uses a system with 22 notes called Shruti, and traditional Chinese music is known for having 5 notes.
So while 12 semitones work well for Western harmony and transposition, it's just one way of organizing sound.
Wow, today's conversation really struck a chord with me. Math really is everywhere, even in music.
I don't hear any practicing going on.
Uh-oh, we're in big trouble.
Let's go get practicing.